Okay, I think we can start. Good morning, everybody. It's a pleasure to introduce you Gloria Montagna, who is finishing a PhD in Barcelona, and she's giving some exercise lessons to support the lectures of Laura Tolosa, the course which started last Friday. So, Gloria, please.
Okay, so I share screen. Okay. Do you see my slides?
Of course.
Okay, so I will present my the solution of the exercises in slides. So I would like you to take pen and paper and solve them at the same time as I do it. So we do it a bit more interactive, and you help me in the steps of that that we need to do to solve the exercises. Okay, if you agree, and I will give you some time in between to do the calculations. So let's start. Today, the first exercise that we are going to solve is to calculate the nucleon-nucleon potential due to the exchange of a scalar meson. In the lectures, Laura did it for the exchange of a pseudoscalar for the case of a pion. And we are going to do the same when the meson that we exchange now is a scalar meson. And if we have time, we start the next exercise in which we will calculate the vertex of a sigma minus going to lambda pi minus from the Lagrangian, the chiral Lagrangian at leading order. Okay. So this is what the first exercise tells us. It, as I said, we have to calculate the nucleon-nucleon potential to the exchange of a scalar meson, and it tells us some things that we can consider to help us in this solving this exercise. It tells that we have to reproduce the expression that was given on the slides. If you remember it, I can show it to you. It was this expression here, right? For the scalar, it's this expression here, the first one. So we need to find this expression here, okay? It also gives us the propagator that we need. In the case of a scalar, it has this form here. It's an I imaginary unit divided by the usual momentum square minus the mass of the scalar meson square. And it also tells us that we have to work in the center of mass frame. That is, if P1 and P2 are the momenta of the initial particles 1 and 2, respectively, and P1 prime and P2 prime are the final momenta of these particles, then we have that the initial P1 is minus P2, that we will call P, and P1 prime is minus P2 prime, which we will call P prime. And with this, we can also define that this will help us in solving the exercise. We can define this K as the P plus P prime divided by 2, and this Q as the exchange momenta P prime minus P. It also tells us that we should work in the non-relativistic approximation. This will simplify our expressions, and this is a good approximation for the case of the nucleon, because its momentum is much smaller than its mass. So we can have that the energy plus the mass of the nucleon is 2 times the mass. And it also gives us the expression of the angular momentum, but that we will be able to identify in our expressions, which is I times K vector product Q. Okay. So this is the diagram of the problem that we want to solve. Now we have 2 nucleons scattering with P1 that we call P, and the incoming second nucleon with P2 that, because we work in the center of mass momentum, it's minus P, right? And then we have an outgoing nucleon, 2 outgoing nucleons with P1 prime and P2 prime that we can identify with P prime and minus P prime, okay? And the exchange sigma meson, the scalar meson, has the exchange momentum that we called Q, if you remember. In the exercise, they told us that P prime minus P, we can call it Q. Okay. So how do we start? We start by writing down the Lagrangian density of the exchange meson, which is given by this expression here, is minus the coupling of the scalar meson to the nucleons times the fields psi prime psi, which are the two nucleons, incoming and outgoing nucleons, and this field of the scalar meson. Okay. Any questions here? So what is the next step that we have to do? We need to know the propagator of the scalar field, and the exercise already tells us that it has this form here, where ms is the mass of the scalar meson, and q is its form momentum. Okay, so now that we know the Lagrangian of these vertices here that we have in this diagram, and we have also the propagator, we can simply, we saw in the lectures that we can simply write the amplitude, which is I times the potential. We can write it as one vertex here, for this vertex here that I call gamma 1. We have to write one vertex here, the second vertex here, and in the middle we have the propagator. This is the expression that we were given in the slides. Okay, and we also have used this short notation for the nucleons, right? UI is U of the nucleon with pi, and U bar I prime is the one for the nucleon with pi prime, to simplify the notation. Okay, and so because we know the Lagrangian, we can see that the vertices are simply given by the Lagrangian once we strip off the fields. So we have that for the case of the vertex of two nucleons with a scalar meson, this vertex has this from here, minus I, the coupling of the scalar to the nucleons. And it's the same for the two vertices, right? For the gamma 1 and for gamma 2. Both vertices have the same form. So what do we do next? We simply can build with these expressions, we can build the two vertices here, okay, with the Dirac spinors. For the first vertex, we have, we introduce this gamma 1 that we said it's minus I decoupling. So we have simply this here, and it is exactly the same for the second vertex. And the Dirac spinors, if we remember, it has this form here is the square root of the energy plus the mass divided by 2 times the mass. And then this here where we have the two component Pauli spinor, this XS, okay, that if we remember, okay, this XS for S equal to 1/2, okay, is simply 1, 0, okay. And for X for minus 1/2, this is simply 0, 1, okay. It's the Pauli spinors, if you remember. Let me erase it. And in the approximation that we work in the non-relativistic approximation, as we said, we have that the energy is very well approximated as the mass because we neglect the 3 momentums. So this goes to 1, this factor here. And here we have that E plus M goes to, it can be approximated to 2 times the mass. Okay, so the spinor, the Dirac spinor simplifies to this here. So we need to compute this U bar, which is simply the transpose times the gamma 0, the gamma matrix 0, which is, as you know, a 4x4 matrix with ones in the first two diagonal and -1 in the second two ones. So if we do this, we take the Dirac spinor and we transpose it. So instead of a column, now we have a vector, okay? And we multiply it with the gamma 0. So what do we get? This simply sign, this gamma 0, what does it just simply change the sign of the second term. So we have the Pauli spinor here, dagger, and here minus the Pauli matrix times the momentum divided by 2 times the mass, and the Pauli spinor. Okay. So now that we know how this U bar looks like, and also the U, we can compute the product, right? Because in the vertex, we need the product of the two. So what do we have? We have the U1 bar, which is this here, but now the spin is S1 for the nucleon 1. And we multiply it by the U1 here. Okay, so what do we get? We have this Pauli spinor times this one here, and we know that the product of the Pauli spinor dagger times the Pauli spinor is 1, so we get this one here. Okay, and then we have this here times this here. Again, the product of the spinors gives us 1, but then we also have this minus sigma 1 p1 prime times sigma 1 times p1 divided by 4 times the mass of the first nucleon squared. And because of the mass of the nucleon is m, we just write it like this. Okay, and also we identified p1 prime, we call it p prime, and p1 we just call it p. Okay, the same for the second one. For the second vertex, we will need the product of the Dirac spinors for the second nucleon, and we have the same expression here. But now we have that p2 prime is minus p prime and p2 is minus p, but minus times minus, we still have the same sign here. So we see that both vertex have the same form. Next, what do we do next? So we substitute this in the expression of the potential, no? We have seen before that we have one vertex, the propagator, and the second vertex. So we have calculated these 2 parts here, so we just substitute it. And what do we get? We get the coupling squared and divided by the propagator, and this I coming from, wait, we have the I from here, from the vertex, right? And we are writing already the potential, so it's I times the amplitude. So we have that I times I gives this minus here. And then we have the product of these things that we were getting here. Okay, any questions up to here?
Gloria?
Yeah.
But you do the non-relativistic approximation in the spinor, but in the propagator, at that point, the Q square has also to be in the non-relativistic approximation, right?
Here.
Yes.
Yes, but we keep the mass of the scalar meson. We are doing the non-relativistic approximation for the nucleons, right? Because their mass is much larger. But for the scalar meson, in principle, we keep it in the propagator.
Well, it's 600 MeV, then okay. Yes, okay.
Yeah.
So you don't do. The point is,
yeah, I don't do it yet. You can do it at the end of the expression if you want. You can do it if you consider that it can be done. But because of the general expansion that we want to find at the end of it, still has this. We'll keep it. Okay. We just do it
but
for
at that point,
nucleons.
the potential depends on energy and time. On energy and momentum, so if you want on time.
Yeah, it depends on energy and momentum.
Okay.
Sorry, I think in the conjugate spinor, the chi diagram should be on the left of the Pauli matrix, isn't it? When you take the conjugate, just in the second line. In the second line of the slide.
This, yeah, sure, probably. Yeah, right. It's true, but when, yeah, sorry for that, it's a typo. But when you take the products of one with the other one, you still get that they disappear because the product gives you this one. Sure. So we also use the static approximation that it was told us in the exercise. So the energy goes to 0. And what do we get? We get this expression here, right? We had this here and we just do the products. So what do we have? We have this one multiplied by this one gives this one here. Then we have this term here multiplied by the one, but also this one multiplied by this, and also the cross one, this all these multiplied times this, and this gives this. Okay, we have this term with these 4 products of Pauli matrices and momentums divided 16 times the mass to the 4, and we have this term here. So we need to compute all these things that appear here. We will do also the change of variables that is proposed in the exercise. This will simplify our life. We take a Q as the differences of the P prime and P, and we also define 2K as the sum of the momentums. So we can see that P prime is K times Q divided by 2, and P is K minus Q divided by 2. We will also use the property of the Pauli matrices that Pauli matrix multiplied by a factor A times Pauli matrix times vector B. It can be shown that it has this form here is the product of the 2 vectors plus I the Pauli matrices times the vector product of the 2 vectors A and B. Okay, so we will use this property here, the Pauli matrices. So we can work the numerator of this second term here, that we see that it's quite complicated, but we can work it out and see what we get. So we have we apply this property here. So sigma 1 times P prime multiplied by sigma 1 times P. This gives us the product P prime P plus I, the Pauli matrices sigma 1 times the vector product. And the same for the other two, okay, for the sigma 2 times P prime, sigma 2 times P, and we get this. And if we further work this expression here, we have what? P prime times P squared. And then we have the this P prime P times this vector product here, but also this here times P prime P. So we can take it a common factor and we get this here, right? And then the product of these 2 second terms. So we have I times I, this gives us this minus sign here. And we have the Pauli sigma 1 times the vector product and the Pauli sigma 2 times the vector product again. And now we introduce the change of variables that we said that we would introduce, okay? So the scalar product of P primes P is the scalar product of K times plus Q divided by 2 times K minus Q divided by 2. So we have that this is K squared minus Q squared divided by 4. And for the vector product also, we introduce this change of variables here. So in the end, what do we get? We get 1/2 of the vector product of Q times K minus 1/2 of the vector product K times Q. So we apply the properties, so we can write it just like this, okay? And we can see that this is exactly the definition that was given us in the exercise for the angular momentum operator, okay? And we see that it's just P prime times P. So with this, we work out the expression that we had before, okay? We had this expression here, and we can identify the P times P prime times P square. It's just K to the 4 plus this here, okay? Then we have these expressions here, and we have this S that comes from the Pauli spinors times this operator that we see here, okay? And we can further simplify it. We can see that we have the square of K square minus 1/2, okay? And then we get this spin orbital factor here, this L times S. And we have defined this, as I said, this total spin has been defined as the sum of the Pauli matrices divided by 2, and we have introduced it in these expressions here. Okay. So now we can do the same for the numerator of the third term. That was sigma 1 times P prime, sigma 1 times P plus sigma 2 times P prime, sigma 2 times P. And we can work this out, and we see that again we have some with the properties of the Pauli matrices, we have some scalar products of the P and P prime, and then some scalar vector products, and we can simplify this, and we see that we get again a product of the angular momentum and the spin that appears here from this definition in terms of the Pauli matrices. And we finally get this expression here 2 times the momentum K square minus 1/2 of the momentum Q square minus 2 times L times S. So we finally substitute all this in the potential. So we had for the first term, we obtained this here, okay? Just what I was showing the second slide here. I just substituted in here in the potential, okay, for the first numerator that we work out and the second numerator that we have also worked out. We substitute all this expression here and this expression here in the expression of the potential. And we can see that what we get is something that looks like this. We have the propagator and the coupling here squared times 1 plus 1 over 16 times mass to the 4th in these products here of momentums and spin and angular vectors, and minus 1 times 4 mass to the square, 2 times K to the square Q squared divided by 2 minus 2 times the spin orbital. So if we analyze term by term, we can see that they are not all in the same, they don't contribute all the same in the non-relativistic approximation. So we will keep terms up to order Q over M, okay? So we see that this term here is going as Q to the 4. This one here, it is going as Q to the 3rd. So these are, we can neglect them. And this one is going as Q to the 2nd to the, to square. So we can also neglect them. And we just also these ones here can also be neglected because they also go as Q to this square, and the main contribution comes from here, from this L times S, this spin orbital moment term that goes as Q, and also this one here that we got. Okay, so we get this and this. And finally, we get the expression that was given to us in the slides once we do these approximations. Okay, so do you have any questions on this exercise? It's mostly a matter of analytic work. Once you know all the approximations that you have to do and all the expressions for the propagator, for the Lagrange and everything, it's just to work it out. And just do it, and you'll see that you get these expressions here.
Gloria, could you just remind the audience which is the relevance of this scalar exchange in the nuclear-neutron interaction, which is the range, where it is important? Just to some phenomenological.
Yeah. Maybe let's go to the slides on the lecture so we can better see it. Exactly, I have it here. So if we remember, we calculated the one pion exchange with Laura. Now we have calculated the scalar exchange now, but you can also do the same as an exercise if you want for the vector or for the row, if you take it as a tensor. And you will get this expression here that Laura was telling us. Okay, for this pion exchange, we saw that it is a long range and it is a tensor force. Then for the scalar, we have obtained this expression here with this -1 and the spin orbital momentum. And because of the mass of the scalar meson is larger than the pion, then the range is shorter. So it acts at intermediate ranges, and it has an attractive central force, this -1 that we obtained here, and this spin orbital force that we also obtain in this term here. And then if you work out these ones here, you can see also that because they are even more massive, the range is shorter. And for the, well, you will see that because we have this one here, it's a repulsive central force, and the spin orbit is stronger than the case of the scalar because it's 3 times this term here. And for the rho, because it's a tensor force, we also get this term similarly that we obtained for the pion. And this was the graphic that Laura was telling us that is very graphically when you watch it, right? At long distances, you have the contribution of the lightest meson, so the pion. At the intermediate ranges, what contributes, it's the sigma basically, because its mass is around 600, so it contributes to middle range. And at short range, you have to take into account the most massive mesons, so the rho meson and the omega mesons is the ones that contribute to this short range interaction.
Other questions to Gloria? Okay, if not, go ahead.
Okay. So the second exercise that we are going to solve is to calculate this vertex here, this sigma minus going to lambda pi minus from the chiral Lagrangian at lowest order. This Lagrangian was given to us in the slides, okay? For the case of the interaction of mesons with baryons, so we can see that there are some B fields that are the baryon fields, okay? And then there are some covariant derivatives that is defined as this here. It's the derivative of the baryon field, but then there is this other term here that is defined in terms of this chiral connection, the so-called chiral connection that has this shape here, okay, in terms of these U fields. And these U fields are defined in terms of the phi, which is the matrix containing the pseudoscalar mesons. So we can see that these terms here, because of this chiral connection, this covariant derivative and the chiral connection in it, we can see that it gives us the interaction between baryons and mesons. But also there are other terms that contribute to the leading order Lagrangian for the interaction between pseudoscalar mesons and baryons. And are these terms here again, where we have B fields and we have these U mu that are also defined in terms of these U and U daggers, so in terms of the pseudoscalar fields. Okay. So, and we are asked to calculate this vertex here, this sigma minus going to lambda pi minus, and show that we have to obtain this expression here for this vertex from this Lagrangian, using this Lagrangian. Okay. So we will see that the first term basically contributes to the process, the scattering process of a pseudoscalar meson with a baryon. And the second and third terms, it's the ones that actually contribute to this kind of vertex, meson baryon going to a baryon, or equivalently, if you change you can do this change, right? Meson and a baryon going to a baryon is the same process as a baryon going to the anti-meson and the baryon. Okay, so, and we will see that these two terms contribute to this vertex here that we would need, for instance, if we want to compute, okay, it would be this kind of vertex, right? Sigma minus going to a pi minus and a lambda. It's this vertex here that we want to calculate. But again, if we use the kind of idea that we used for the previous problem, that the interaction is mediated by the exchange of mesons, right? So we can just join this vertex with another one like this here, like, okay, sigma minus going to lambda, and compute basically the scattering of a sigma minus going to a lambda with a lambda by the exchange of a pi minus, okay? It's fine. Okay. Okay. So what I told you that the B is contains the baryons, but what is the shape here of these fields? It is in SU3 because we are using chiral Lagrangians that are defined in SU3. These B matrices look like this and contain the baryons of the octets. We can see that there are on the diagonal, there are the sigma 0 and the lambda mesons, the non-charged baryons, sorry. There are the non-charged baryons, and then in the diagonals, we have the rest of the baryons of the octet, the sigma plus, the proton and the neutron, the sigma minus, and the cascades. And this phi that was entering through this U field exponentially, as we have seen before, okay, this phi here that is entering exponentially in this U here in the Lagrangian. This matrix contains the octet of pseudoscalar mesons. So in the diagonal, again, the non-charged hadrons, in this case the mesons, the pi 0 and the eta. And in the non-diagonals, we have the pi plus, the pi minus, and the kaons and anti-kaons. But we want to particularly calculate this vertex here. So a sigma minus going to a lambda and a pi minus. So we don't need to take the full matrices because our life will be very complicated. We just need to take in these matrices that fields that we are interested in and consider that the rest are 0 because we will not take the terms that go with other fields that are not these ones that we are interested in. So for the B, we will have only the sigma minus field, which is because it's these fields are these annihilation fields, okay? So it's the entering baryon in the vertex, it's the sigma minus. And then in the Lagrangian, we see that we also have some B bars. These are contain creation fields. So the ones that we have in the right side of the vertex. So we see that we keep the lambda here in this matrix here. So we get this expression here for the B bar. And then we also want the phi bar because, again, we have a pi minus going out from this vertex, okay? So we want this. But in the Lagrangian, however, we have this u defined in terms of phi, not phi bar. But we can see that this vertex here, a sigma minus going to a lambda pi minus, is the same as if we would have this other vertex here. It's the same to calculate this vertex here than this one. We should get the same expression from the Lagrangian. So instead of this phi bar here, we can just take phi, where the annihilation of a pi minus would be the creation of a pi minus is the annihilation of a pi plus or a pi minus bar. We will keep this notation, this pi minus bar, because we have this pi minus in the vertex that we are interested in, okay? Any questions up to here? Okay, so next, what we have to do is to expand this use in terms of the meson fields. Okay, we know that the expressions for this u and u dagger in terms of these meson fields are exponential, so we can just expand the exponential in terms of these fields. And so the a to the x, okay, we know it's 1 plus x plus 1/2 x squared, okay, the expansion of the exponential. So for the u field, we get this 1 plus I times the phi field divided by the square root of 2f, then minus, because we have this x squared, so I times I gives this minus here, the field, the meson field square divided 4 times f squared. And for the dagger, the same, but now we get this minus here, okay. And now that we know how these expressions, this u and u dagger look like, we can introduce them in the definition for the chiral connection. It was given in the exercise that it's defined as this, as 1/2 u dagger, the derivative of u, plus u, the derivative of u dagger. Okay, so we just substitute these expressions that we got here, okay, for the u dagger and the derivative of u. And for the second term, u, the derivative of u dagger. And now we have to remember that these fields don't commute with each other. So when we take the derivatives, we have to take in mind that for this, the derivative of this term here, for example, it's the derivative of the first field times the second field plus the first field with not derived, just the first field times the derivative of the second field. We have to take in mind that they don't commute, so we have to act on the derivative on each of the two fields. Okay, and the same for the second term here with the u dagger. Okay, oh, so here there was a typo. Okay, so we if we do these products now here, and we will try to keep the less number of fields in our expressions, we see that we have to take this 1 times these 2 terms here. This gives us this here, but we have contribution from a derivative on the phi field times a field. And we see that we also get this kind of terms if we multiply this term here times this one here. So this term we also have to take it. And the rest of the products just would give us a higher number of fields, so we don't take them. We just take these ones here, just the ones we need. For the other, the same. And we can see that we can simplify this. Okay, this goes away with this. And if we simplify this, what we get for the chiral connection is this expression here. Okay, it's 1/4f squared. Phi, the derivative acting on one, and minus the derivative acting on the second one, times the field. And this chiral connection, we computed because we need it to compute the covariant derivative. It has this expression here. Okay, so we can just see that for the covariant derivative, it looks like this. Okay, it's the derivative of the baryonic field plus 1/4f squared, and then we have this product of mesonic fields and derivatives of these mesonic fields times the baryonic field, and the opposite because we have this commutator. Okay, so chiral connection times the B field minus B times the chiral connection. But we also need to compute this U mu, okay, that we saw that it's defined as like this in terms of the anti-commutator. So we do the same, okay, we expand, we expand this U and U dagger in terms of the exponent that is given in terms of the exponential of the mesonic field. So what do we get? We have the U dagger here times the derivative active acting on U minus I times U, the derivative acting on U dagger. We introduce the derivative, remembering that the mesonic fields don't commute, so we have the derivative on the first one times the second one plus the first field, the derivative acting on the second. Okay, this is important not to simplify these kind of terms. And the same for the other terms. If then we work out these products, and again we keep the terms with the less number of fields that we need, as far as they don't cancel each other, of course. So we have this this one multiplying these two terms here gives us this, but we also have the contribution of the product of the second term here with this derivative term. Okay, and the same for the rest. So we can see that some terms cancel, but we keep the rest that don't cancel with the minimum number of fields. And for this U mu, we get this expression here. Okay. And okay, so we see that we get this expression here, and we can compute the terms that were appearing for the Lagrangian. There was a term with a constant D and a term with a constant F. If you remember, the one was with the anti-commutator and the other one with the commutator. And if we just substitute this U mu in this expression here, we get this here. Okay. So yeah, I think I would leave it here. Maybe if you have some questions, because now the calculations are a bit long, and maybe we can continue it tomorrow. Do you have any questions up to what we have done up to here?
Yes, hello.
Yes.
I just for the expansion of the exponential,